Good afternoon, everybody. It's my pleasure to welcome you to our tutorial today towards better explainable AI through genetic programming. So today, myself and my colleague, Dr. Yi Mei, will be presenting this tutorial. We are both from Victoria University of Wellington in New Zealand, and we're in the Evolutionary Computation and Machine Learning Research Group. I will be presenting the introduction to the tutorial, talking a little bit about the XAI concepts, and then my colleague will take over and talk more about the introduction to genetic programming. So if you're not as familiar with GP, don't worry, we'll do sort of a GP 101. Yi will then talk more through some of the interpretability methods in GP, and then I'll take over and finish off on that bit, and then talk through some challenges and future directions at the end of the talk as well. Now, even though we can't be there in person, we are here with you now, hopefully, and we're more than happy to answer your questions either at the end or as we go, depending on how this has been run. So I'll kick off with introducing XAI. Why do we need interpretability in AI systems? I mean, there's kind of an interesting history to this in that a lot of early systems were themselves interpretable. They were based on expert systems where we had manually designed logic and rules, and so they could be understood. But as we all now know, these approaches were not very effective, and they're quite brittle against real-world complex problems. The performance wasn't what it needed to be. And more recently, machine learning, and particularly deep learning and other such advances have been really sort of powerful in terms of their performance in these tasks. But that high performance comes at a cost, that cost being the lack of interpretability of these models. So we see every day that there's a new deep neural network with billions or even trillions of parameters now, and if you have that many parameters, then there's just no way that you can understand what's going on in that. And as AI becomes more and more widespread in our society, we are seeing more and more concern about the lack of interpretability, especially when we're starting to see machine learning being used in sensitive applications, and this people and citizens are quite rightly getting concerned about how it's used. And so interpretable AI is a sensible next step to try and advance the field further. And this very much, a lot of this conversation started with DARPA and some of the work that they did, quite a few last century now. So it's been discussed for a long time, but certainly getting more popular these days. So why else do we need it? So to identify what we call clever hands predictors. So clever hands was a horse in the 20th century in 1907, I think. A horse who could do things like add up numbers and perform puzzle tasks and so on, and this really amazing horse. But it turns out that the horse was actually just watching his trainer, who was giving him subtle clues about what to do. And so a clever hands predictor in this context is where we have an AI model that is picking up on things not related to a task at all. So the classic example over here is when we are trying to classify a husky as a wolf. We would think, looking at this picture, that we would be looking at things like the eyes and nose, the snout and the ears. But in fact, when you do some analysis, what it's detecting is snow. So the model has learned that wolves are more likely to be in snow than dogs are. Therefore, by detecting snow, it can detect wolves. And until we have this sort of explainability, we don't realize that the model is perhaps not actually doing what it says on a tin. And of course, enhancing trust and confidence, providing new insights. So if we can understand models, we can then advance the science behind them better. And even legislation these days. So the EU's GDPR has a lot of sort of stringent regulations around the use of technology in general, and even AI and so on. And there is quite intuitively this trade-off between performance and explainability, right? So we know that deep learning is very good in terms of performance on many tasks, but is very hard to explain, whereas something like a linear regression model or decision tree is relatively easy to explain. It's interpretable, but it's not as effective. And so there's this sort of trade-off that we have. And you can sort of plot this on a graph and look at the different machine learning methods and how they might have that different trade-off. I should note that we talk both about explainability and interpretability in this talk, and that is kind of used interchangeably on purpose. They're not defined specifically in literature. This is a new field, and very much they often are used to mean the same thing. So that's quite purposeful if we don't define them very separately up front. And of course, what we want to do is to improve the learning performance and the explainability of models, preferably at the same time. So if we can create new XAI methods that are much more explainable, but also more performant, and then that's clearly the ultimate goal. And there's a variety of different ways that we can go about this. So for deep learning, changing deep learning methods to learn more explainable features or representations, interpretable models. So we have models that can themselves be learned to be more interpretable. And then also things like model induction, where we take a complex model that we've trained through some algorithm, and then we try and approximate it with an explainable model. So maybe you take your deep neural network and you build a decision tree to approximate it. And by doing that, you can perhaps not quite get as good performance, but get much more explainability. And so there is the sense in the field that having more explainable models and simpler models could also lead to better performance, because you have fewer parameters to train and you better understand your model and how to improve it further. So at the moment, when we talk about XAI, we very much talk about trying to understand the system's overall strengths and weaknesses. But there's also, if we look into the future, we also think about systems that could perhaps identify their own strengths and weaknesses in sort of a more autonomous way and then correct its own mistakes. So the better we can understand AI machine learning models, the better we can design them so they can self-correct as they train. And yeah, at the moment we have sort of, these very complicated models that look something like this, where it tells the user, this is the cat with 93% probability. And the user kind of says, why? I want to understand why it thinks that. When can I trust it? When won't it work? And perhaps tomorrow or sometime in the future, we'll have these explainable models that can tell us, this is the cat because it has furs, whiskers, and claws. And in particular, it has this feature here with these pointy cat ears, very distinctive for a cat. And within interpretable or explainable machine learning, we have, as you can imagine, many different techniques. And quite a useful categorization of those techniques is into intrinsic and post-hoc, and also into global and local. And we'll go through each of those in a little bit more detail. So intrinsic methods are those that construct self-explanatory models. So if you think about a decision tree or a genetic programming tree, rule-based models, linear models, they are explainable or interpretable just as a function of how they are built. Whereas a post-hoc approach would be where we take a really complex model and then we try and create a second interpretable model to explain it. So we take our deep neural network and we try and approximate its behavior to understand how it might be operating inside the black box. Global interpretability and local interpretability are more from the point of view of what we're trying to understand. So in global interpretability, we want to understand the overall model structure or behavior. And in local interpretability, we're trying to understand one particular decision that the model has made. And you can imagine in different cases, you may want one of these or the other. So if you're a researcher in machine learning and evolutionary computation, you perhaps are very interested in how to improve your model or your algorithm to do better on a whole bunch of different inputs. Whereas if you're a client for a bank and the bank is using a model to decide whether or not you get a mortgage, you're really only interested in your particular decision. So why has the bank rejected my loan? What are the reasons for that? So that would be local interpretability. So we'll talk through each of these categories and give some examples of these in more detail. So firstly, the intrinsic and global interpretable methods. Again, these are ones where we train self-explanatory models directly. models such as linear models, rule-based systems, decision trees, and so on. And we generally will add some sort of interpretability constraint to it. So when we're training the model, we say, for example, you can use no more than 10 inputs, or you can not have more than 5 layers in your GP tree, or things like that. And so we want to try and find this trade-off automatically within the model training itself. And very much this can be a multi-objective problem, where accuracy and interpretability are often conflicting. It's very hard to get the most accurate model possible without it getting overly complex, and vice versa. If a model is too simple, you're not going to get very high performance in many cases. There's some sort of middle ground there. And so here we're really training models that are intrinsically interpretable across all inputs. So small compact trees that might look something like this, for example. In contrast, intrinsic local interpretability is where we are creating models that can explain particular decisions they make for particular inputs, just by nature of how they are trained. So a good example is the attention mechanism in recurrent neural networks. So recurrent neural networks use this idea of attention to say, to sort of focus on parts of an image that it's generating an output for. And we can visualize this attention rate matrix to understand the predictions. For example, here, where we are generating the captions, a woman is throwing a frisbee in a park, we may want to explain why frisbee has been chosen as this particular word here. Now, if we look at the attention rate matrix for that word frisbee, you can see there's, with this lighter coloring here, that the attention rate matrix has much higher values or higher coefficients for this area of the image, where in fact it is a frisbee. And so by seeing that, we can say, all right, this makes sense. It's focusing on that part of the image that we would expect it to. In contrast to our huskies and our wolves, where it perhaps would have focused on the snow when it shouldn't have. But of course, this is also quite good for understanding incorrect predictions. So a large white bird standing in a forest. No, this doesn't look much like a bird. Why is this model thinking it's a bird? And if we look at what it's focusing on, you can kind of imagine yourself that this could look kind of bird-like to a deep neural network. And similarly, a woman holding a clock in her hand. For the clock word, it's focusing very much on the circular area of her jumper. Again, this pattern looks a little bit like a clock. In contrast, post-hoc interpretability is where we're trying to, again, understand a trained model, a trained complex model, and understand how it operates. And within post-hoc methods, we often talk about model-specific or model-agnostic methods. So model-specific ones being ones that are trained for a specific type of algorithm, for example, deep learning, and a model-agnostic being one that can explain any model or a large number of different types of models. And again, we'll talk through each of those just in a little bit more detail. So post-hoc global interpretability, an example of a deep neural network one, would be this approach here. So if we want to understand how our deep neural network works, one approach we can do is try and find the image that gives the highest score for a particular class label. So if we consider this bottom image here, so we're trying to maybe one of the classes of our network is predicting is a goose, so a type of bird. Then we can say, what is the image that gives the highest score for goose? You know, what image out of all the possible images there could be will give us the biggest prediction for goose? And then that will give us a global explanation in terms of why it's predicting goose. And when you run the algorithm and evaluate this, you find that it gives you something like this. So this is the image that looks most like a goose to the neural network. Obviously, it's not a real image, it's a synthetic image that maximizes this function here. And you can see that there's a number of different goose shapes in the image in different locations, which suggests that the neural network is looking at different parts of the image and saying, you know, is there something goose shaped in there? And this sort of explanation may well then lead you to think, hang on, this behavior would, for example, miss a small goose up here. And so you can start to understand what it might fail on, as well as what it's able to classify correctly. In terms of a model agnostic approach to post-hoc global interpretability, things like permutation-based feature importance is a really classic example. So if we have our baseline accuracy of a model on a test data set, we can then look at our features in that data set and permute them slightly one at a time. So if we change the input, the feature values for max concave point, how much of an effect will that have on our classification accuracy? If it has a very small effect on the classification accuracy, then probably it's not a very important feature. The model is not using it to a very high extent to do the classification. Whereas if a big change happens, then we probably think that in fact it's a really important feature, and so the model is heavily reliant on it. And by doing that across all of our features, we can then sort them and look at the correlation between them and say, okay, these must be the features here that our model is most focused on when making predictions. In terms of post-hoc local interpretability, again, taking a deep neural network as an example for a model-specific explanation, approach here is to try and simplify the image and see how much we can simplify it before it changes the classification result. So if this is our instance here and it has a class label of bedroom, then how much of that bedroom picture do we have to remove in order for it to not recognize it as a bedroom anymore? And you can see with all the sort of clouded out parts here that when you're moving a separate of bed, it will no longer classify it as a bedroom. It'll probably classify it as a bed instead. And that again validates our trust or our understanding of how we think the model might operate. Because very much if I look at this image and I can't see the surrounding environment, I would say it's a bed. I wouldn't say it's a bedroom. And you can see that for the other examples as well. In terms of a model agnostic approach to local interpretability, the most well-known and popular approach is what this method called LIME, which is uses a linear sort of proxy to try and evaluate how these complex methods work. So it's model agnostic. It shows what features were most influential in the model making a decision. And it's formulated in this way, which looks quite complicated, but when you look at how it's broken down, it's actually reasonably intuitive. So we have a loss function based on the prediction error of the model, the class of the model we're using, and then the local neighborhood size. So this prediction error here is saying that we want to make sure the prediction by the LIME algorithm is as close to our original prediction as possible. This G here is just saying, what model are we using? We want to find a model that best minimizes the loss function. And then this neighborhood size is saying that we want to pick the appropriate neighborhood size to explain it correctly. And then we also have this task-specific model complexity. So, for example, the number of words in a natural language processing task, number of pixels in image processing tasks that are being used by the algorithm. And so we want to minimize both the error of our proxy method, our LIME output, as well as the complexity. And so how do we actually go about this? So it's a local method. So we select a single instance to analyze and explain. We add some noisy points around it. So if this is our one we're trying to explain here, we'd be adding these noisy points around the spread around the instance. We then rate the points by how close they are. Points that are closer to an instance we're trying to explain are likely to be more indicative or more representative of it. And then we train an interpretable model. So something simple like a linear model to try and recreate the predictions of our classifier. And then by interpreting the local model, for example, if we're using a linear model, we can interpret the coefficients of the model. So very high coefficients, meaning there's a big effect on the model's output. And then by that, we can understand what are the major factors being used by this model to make the prediction. So if we have a complex model here that takes in a data set which is somebody's medical history and predicts a disease, so do they have influenza or COVID perhaps, we can then feed this data into our explainer, which will then say, hang on, these are the most important factors in making that decision. So if they have a sneeze and a headache, but they aren't so tired, that is why I'm predicting it's a flu. And so based on that, the human can then go, well, do I trust this prediction or do I not? Does that seem like it makes sense to me? And very much this is the sort of thing that medical doctors are quite interested in terms of if we were to use machine learning in these spaces. Now, that's a little introduction to XAI, and hopefully that gets reached your appetite, so to speak. And now I will hand over to my colleague, Yi Mei, to continue talking about GP.
Okay, thank you, Andrew, for your introduction to XAI in general. Now I'm going to introduce GP briefly. GP is a type of evolutionary algorithm. The difference between GP and traditional evolutionary algorithm is actually it involves computer programs rather than solutions. So GP has the same framework as the other genetic algorithms. The main difference is in the representation. So particularly, GP can have the tree-like or graph-like or linear structure of its individual representations. So you can see in this big tree, actually it represents a program shown here, and it can also represent a calculation program like this, max. And the last one is a linear representation, and this is similar to what we actually write the program, instruction by instruction. And here we particularly focus on the tree-based representation because it is the most commonly used representation in GP. And it has a terminal set and a function set. The terminal set includes the inputs of the program and usually also has some random constants to represent the coefficients or other arguments that needed in the program. It has no argument, and it will form the leaf nodes of the tree. The function set contains the operators to process the inputs and output the results. For example, the arithmetic operators and logic operators could be the function set. And if we want to generate a GP program, we start from the root node, and every time when we need to sample the value of the node, we randomly sample from the terminal or the function set. If we sample from terminal set, then we stop this branch. Otherwise, we create the child nodes of the function and recursively sample its children. So here is an example. If we start from the root node, we randomly sample, we get a plus here, and we know plus has 2 children, so we recursively randomly sample its 2 children, left and right. So the left, we randomly sample, we get the multiplication here, and it still has 2 children, so we recursively sample, and now we sample x for the left child and 1 for the right child, and they are both the terminals, so we don't sample their child anymore because they don't have the child. And then we come back to the right child of plus, and we randomly sample y here, and we stop the whole generation, and we get this program, x times 1 plus y. So the terminal and function sets are very important for GP, and sufficiency and closure are critical, the 2 critical conditions for the success of GP. For the sufficiency, that means the terminal and function sets must contain a combination of the terminals and functions so that it can form the solution or the optimal program of the problem. And closure means any function can take the input of any other functions or any other terminals. So this is a kind of type. For example, if we have a logic operator that can only take the Boolean arguments, and we have a plus, then it doesn't satisfy the closure, because the plus will provide output a real value which might not be able to be the input of the end. So these two are the critical conditions. And GP genetic operators, crossover and mutation, are tree-based, and the crossover basically randomly select two trees and swap them. And the mutation randomly select the subtree and replace it with another randomly sampled subtrees. So these are the typical genetic operators used in the tree-based GP. Later on, we will introduce some other genetic operators that, if we consider explainability or the model size and complexity into account. So GP can be used for different machine learning and optimization tasks. One typical example here is the symbolic regression, such as natural law discovery. So if you look at this example natural laws, this is a physical experiment of pendulum, and the model can have a complex structure and also coefficients. So if we don't have enough domain knowledge, it's hard to assume the correct model structure, but GP can help automatically find proper model structures. So to do symbolic regression, we need the training data, x1, xn, and y is the target output. We have the terminal set, usually the input value, the variables, and some random variables, and the functions, whichever operator that we think should be in the model. And the finish function can be the mean squared error or any other loss function in regression. And the initialization, we have this standard initialization, grow, full, and ramp and half. And we have the breeding process. We have the elitism, tournament selection to select parents, and we use the typical tree-based genetic operators, and then we generate offspring to go to the next generation. GP can also do classification, and in particular the binary classification. And the idea is very simple. GP outputs real value, and then we set a threshold here. And if it's smaller than this threshold, it's class 1, otherwise it's class 2. So we can translate the real value output into the classification. And it can also learn decision-making policy. This is becoming popular in recent years and quite closely related to reinforcement learning. So some examples, dispatching rules in job shop scheduling, and we see recently also some people using reinforcement learning to learn dispatching rules. And the routing policy, in vehicle routing, we use a policy to guide the vehicle to serve the customers in a dynamic environment, such as, we have new order coming, and how we incorporate the new orders to the drivers that are already on their road. And here, GP is actually to learn a priority function to calculate a priority or score of the candidate tasks, such as jobs and customers. So the main process is we use a set of training data. So this is the same as traditional machine learning. We use training data, but here we use problem instance rather than those classification or regression data sets. So here we are trying to solve a problem, such as a vehicle routing problem or scheduling problem. And the terminal set includes the state attributes and also the constants, such as where the vehicles are or whether the machine is busy or not. So these are the state attributes. And the fitness function is based on a simulation, or here we can also call that a meta algorithm. And we use this simulation to generate a solution by a GP rule or policy and calculate its objective value, such as the total cost, max span, and total time that we are interested in minimizing, and set that as the fitness of this GP policy. So this is a overall flow of the evaluation. We can include this fitness evaluation model into the GP process. This is how we could use GP to learn the decision-making policy. And now I'm going to introduce how we could achieve better interpretability through GP. So the ontology of Xgp, we can divide it into three main categories: the intrinsic Xgp, post-hoc Xgp, and the GP with visualization. The intrinsic method is basically the same as the intrinsic XAI method. We evolve GP and consider the interpretability during the evolution process. So we're trying to evolve a model that is both good and also interpretable. And this is a major part in this direction. I will be mainly talking about this part in this tutorial. And post-hoc Xgp, mainly after we get the GP model, we can explain it. But we could also use GP to explain some other models as a post-hoc approach. And visualization is we take advantage of some visualization technique to improve the interpretability of GP. So these two parts will be covered by Andrew later on. I will talk about these five one by one: GP with program size reduction and better model complexity, dimensionality reduction, interpretable program structure, and also interpretability measure learning. First, GP with program size reduction. And this is actually not a new topic. It has been studied for years in the GP community, but probably not explicitly consider the interpretability. When evolving GP, we know that GP could grow unnecessarily large, and this is called the bloat. And there are a number of bloat control methods that could reduce the program size. And although these studies didn't explicitly consider the interpretability, it's reasonable to believe that with a smaller program size, the model could be more interpretable. So I included most of the bloat control methods here, but also some latest methods that consider interpretability. So first, the simplest approach is just to limit the depth or size. And this has been commonly used in most algorithm design. We need to set a maximum depth or maximum size of the GP program. Otherwise, it will grow infinitely large. And the parsimony pressure is another very commonly used bloat control method to evolve both effective and small GP programs. And it can contain different methods, the Tapian methods. The idea is that if an individual is too large, if we set a threshold, which can be the average size of the population, if it's larger than that, then it will get a very bad fitness, regardless of how good it is. So it's a kind of death penalty. And we can also use the linear parsimony pressure. And we define the fitness as the raw objective value, such as accuracy error, plus a penalty related to the program size. And here, the alpha coefficient is very important. to control the balance between the raw objective and the program size. And lexicographic, we can divide the individuals into different buckets based on fitness. So we have, fitness 1, fitness 2, fitness 3. We have different categories of fitness as the subset or bucket. And we can select the individuals. And when we are comparing the individuals, we first compare the rank of the bucket and whether they are in the same bucket or not. And if one individual is in a better bucket, then it wins. Otherwise, if two individuals are in the same bucket, compare them with the size. And the double tournament is similar, but has two tournaments. The first tournament selects the candidates based on fitness. So if we use if we use the tournament size of 7, we will select 7 individuals randomly and select the one with the best fitness. So this first tournament is actually the same as the traditional tournament selection. But there is another tournament after the tournament selection, the first tournament. So in other words, if the second tournament selection has a size of 7, then we need to do the first tournament 7 times, which means actually we randomly sample 49 individuals in total, 7 times 7. And then first tournament, we do it 7 times to get 7 individuals. And these 7 individuals will be the candidates of the second tournament. But the second tournament actually selects based on size instead of fitness, so that we can consider fitness and size by the 2 tournaments. We could also use 2-stage methods. In stage 1, only the raw fitness is considered. And after that, stage 2, we consider program size. And the Pareto-based perceiving pressure, we just consider 2 objectives. One is the raw objective and the other is the program size. However, the issue here is if we consider these 2 objectives and we just use the traditional multi-objective algorithms to solve it, an issue is that it's much easier to get a small program that's performed quite bad than a very good program, which might be large. So the population, if not evolved properly, if you just treat them equally important, is actually more and more small programs dominate other programs, and then we will shift to the small but actually not so good programs. So this is a kind of selection bias to the small program set, simply because if you randomly generate, random sample is much more likely to sample those individuals and survive. To address this issue, we can consider alpha dominance. And this alpha dominance is an extension of traditional dominance relation, which can, if we can tune this additional alpha parameter, we could have a more flexible bias towards the raw fitness or performance and the size. For example, if alpha is 0, then it's the standard one, like this one. And then if it is infinity, then we don't really consider the size. It's just the single objective with the effectiveness. So if we set alpha somewhere in between, we can have a better control of the balance between the effectiveness and the size. And we can also adapt the alpha parameter, because the alpha parameter is very important to control the balance, and it's a bit hard to set it to a fixed value during the whole evolutionary process, but we can also adapt alpha here. And some ideas here is we can use the linear adaptation, like this one, from large to small, that will gradually shift from effectiveness to size. We can also use the sigmoid is similar to the two-stage framework. In the first stage, consider the effectiveness and gradually shift the bias to the size. But this shift is quick. And we can also use some other ideas like cosine, this back and forth is more like, I change my bias to effectiveness and then size and back and forth. So some idea of the alpha adaptation. And we did some further work to automatically learn how to adapt alpha, and this is based on the boundary of the population that we found so far. For example, if you look at this, previous individuals here, and then the blue current parallel front, and from this distribution, it seems like this current population is good in size. If you look at this, the size improved a lot, but the effectiveness is not so improved. So we probably adapted the alpha to focus more on the performance rather than the size. So we want to push the population to this direction. And next strategy is the breeding. So we can also control the program during the breeding process. And the idea is to design genetic operators to control the program size. The traditional operator has an issue that it is possible to replace a small subtree with a large subtree and then increase the size of the overall tree. So here we can define different crossover mutation operators to reduce this negative effect. The one-point crossover here is to select the parts whose parents have similar shape. For example, here, we would select these two subtrees to cross over because their parents, they are both the children of the root node. So if we swap these two, it would not change the overall parent size so much. It might increase the first parents a bit, but at the same time it will reduce the size of the second one. And they might have the similar role in the tree because they are their parents have similar shape. And the point mutation is not actually replacing the subtrees anymore. It's just to mutate a single node, for example, from plus to minus. So it would not change the size of the parents. And the uniform crossover is similar to the one-point crossover. First, it will look for the common regions, and then each node in this common region could be swapped with each other. But we only swap the nodes at the same position in the common regions. So it will keep the shape of the two parents as much as possible. And the size fair crossover, we randomly select the first crossover point from the first parent, but for the second crossover point, again, we want the swapped subtrees have the same similar size. So this, again, could keep the size of the offspring most similar to their parents. For example, if we select the first subtree from the first parent, and then we can select any of these, similar size subtrees. And the next crossover is the homologous crossover. This one is quite similar to the size fair crossover. The difference here is, in addition to considering the size of the subtrees, it will also consider the path of the subtree to the root node. And it will select the subtree whose path to the root is most similar. So for example, in this second parent, actually we have these two subtrees with the same size. If we use size fair crossover, we just randomly select from them. But if we use the homologous crossover, we would select this first one rather than the second one, because the first one has a more similar path to the root node. And we have the operator equalization, and this is to trying to achieve some kind of desired distribution of the program size in the GP population. For example, we want the program size of the population to be uniformly distributed, and if the current population is shifted, is different from this target population, then we will set different probability to different program sizes to accept the offspring. So if the offspring can make the distribution closer to the target, then we'll accept. The next strategy for program size reduction is the explicit simplification. Idea is to prune the tree and remove the redundant branches. Here are some considerations. When to simplify the tree, we can do it every generation or in the final generation or at some every 5 generations, something like that. And which individual to be simplified? We can randomly simplify, we can simplify all the individuals, or we can simplify only the good individuals, or we simplify the parents for the crossover mutation. And how do we simplify? We can use the genotype, such as the A minus A, we simplify to 0, A divided by A simplified to 1. So these are the structure. Or we can also consider phenotype or behavior. For example, if a subtree always output close to 1, 1.001, 0.9999. So every time it's very close, then we could simplify it to just 1. So the basic idea here, algebraic simplification, and this is to consider a large number of algebraic rules to convert the subtrees. And this is the most straightforward idea to simplify the trees. And the results are quite promising: faster training time, and also small program size without worsening accuracy. And the evolved rules are more interpretable. And we can also consider more logic operators instead of the algebraic operators, such as if we have the mean A plus B, if B is always non-negative, we have some domain knowledge, we know that B is always non-negative, then we can simplify it to A. And numeric simplification is based on the phenotype, the behavior. There are some ideas here. For example, if we have this tree, and we can say, oh, this A is B plus C, and we can see if we from the training data, we see the minimum value of C is -10, and maximum is -7, 7.3, and the range of node B is actually from 0.02 to 0.027. So it's much smaller than C. And it's like the value of A is dominated by node C, and node B kind of very little. So in this case, we can say, okay, we just simplify this subtree to C. And this example, node D is actually E divided by F. Again, we can see this from this calculation, the training data, we can see, oh, the range of D is very small, from 2 to 2.0015. And in this case, probably just simplify it to a constant. And constant is the middle value of its range, because its range is so small. And there's another idea. Based on the phenotypic simplification, we design a GP method based on niching. So we can cluster the GP trees based on phenotypic behavior. So we group the GP trees showing similar behaviors together into the same group. And we simply replace a tree with the smaller tree or the smallest tree in the group. And we can replace the whole tree with a smaller tree, but showing similar or almost the same behavior. And here we use niching to group the GP population, and we use an external archive to store the smallest GP individual in each group. And we use the multi-source breeding to select from the original population and the archive, so that it's like we simplify the parents from the original population with the archive, with the small individuals in the archive, so that we can generate smaller offspring. And we got quite promising performance. And this blue one is the result of the new method. And we compare with other parsimony pressure methods, we can see we can achieve the best performance. We compare with others. So performance is actually very important. So we got the best performance among all the compared algorithms. We can see that these two are the Tapian and LPPP. I couldn't remember this, one of the parsimony pressure algorithm. And they actually got a smaller size. However, their performance is much worse. So overall, the blue one still gets the overall best results. Okay, next, we consider better model complexity in GP. Previously, we just consider program size, which might not be comprehensive enough to say this is more interpretable. Actually, we received some feedback saying that smaller program doesn't mean it's more interpretable. Yes, we agree. So model complexity might consider more information that could reflect the interpretability. For example, the plus minus has a smaller complexity than the tangent or abs, or if they are harder to explain or have a higher complexity. So if we set different complexity measures rather than treating them equally important, if we just count the number of nodes, we could get some different measures for the complexity. So this one is to define different complexity measures for different functions and also terminals into the multi-objective GP. And this is used to learn the reinforcement learning or Monte Carlo policies, and got some Pareto front here. So we can see complexity 1, 3, 5, 7, so different model complexities. And we can see different models in the Pareto front. And this seems to be quite interpretable. And there are other model complexity measures. For example, this one actually defined another more theoretical complexity measure, which can prefer flatter trees rather than deeper trees. In other words, it has the fewer nested functions. So this is a good sign, because if there are many nested functions, it makes it harder to explain. So yeah, I'm not going to go into details of this, but this is how it calculates the so-called nonlinearity complexity to achieve the preference to the flatter trees over the deeper trees. Another model complexity measure here is the VC dimension. And VC dimension is a very commonly used statistical learning complexity measure. And here we can use the VC dimension as a penalty in the fitness as the structural risk minimization. And we can estimate the VC dimension of the GP model, which is a big challenge. But this paper has a big contribution in estimating the VC dimension efficiently and use it as the fitness during GP process. And it ran on some symbolic regression problems to show, okay, this is quite much simpler than the models obtained by other GP methods. Okay, next strategy is the feature selection. Interpretability also depends on the number of features in the model. If there are too many features in the model, it also makes it hard to explain. So we want to make it as few features as possible. We know that GP can do feature selection by itself. However, it's also sometimes not enough. And especially the original feature set is very large. So we might not be able to get enough small feature set in the GP model. So we might need stronger and explicit feature selection. And to do this, a key issue here is actually to estimate the feature importance, which usually doesn't exist in the data itself, and we need to estimate it during the GP process. So first is the permutation importance, and this is based on the permutation test. First, we can run GP to get a good model, and this can be a separate run, pre-run. And then in this good model, we can calculate the feature importance based on the permutation test. Something like this. We permute the value of the feature in the GP model and see whether the model performance will change much or not. And this is the feature importance. And from there, we can calculate the importance of all the features, and we select feature based on that. For example, we can say, okay, here the feature's importance defined like this, and if it's larger than 0, then we select it. After we select the feature, we run GP again, but this time with only the selected features, and we can get another model with a smaller number of features. So this is the feature selection step in this whole process. And the results, we show some good results, better generalization here, and also these are the feature importance, and we can see, this is much smaller number of features selected than this one. And in addition to the symbolic regression, we also apply that to test on the job shop scheduling to evolve decision-making policy or dispatching rules. And we also achieved the promising results. We got 18 features originally, and we can select 6 out of them, which is less than half. And also the performance is improved and it becomes more interpretable. And further, one issue here is actually we need to run many GP runs. Usually one GP model is not enough to have an accurate estimation of the feature importance. So we need a diverse set of GP models. So can we make it faster? Can we speed up the process of data collection, the good GP models for the feature importance test? And we can use a single run rather than multiple runs, and we can use niching to obtain, multiple different GP models. And we can also use the surrogate to speed up the evaluation. So in this case, we run GP with the niching and the surrogate, and we do the feature selection based on the permutation test, and we run GP again with the selected features. So we tested on, again, the dynamic job shop scheduling problem, because this fitness evaluation is very slow. So we replaced the original simulation here with a much quicker, much smaller simulation with only like 1/5 of the size of the original simulation. And we used the niching here, particularly we used clearing approach for niching. And we find out it can automatically select a good subset of the features, and mostly better than all the features, and sometimes even better than the current best known feature subsets. And these selected subset by this two-stage GP actually make sense. They are all quite important features for the dispatching rules that's from our domain knowledge. And later on, we further extend this algorithm to consider the evolved individuals in the feature selection stage as well. Previously, only the selected features are used in the second GP. But here we say, okay, why not? We got the individuals for the feature selection. But can we also use the evolved individuals to speed up or to help the second GP run? And yes, and we can use it based on some individual adaptation, because the final individuals in the first stage contain all the features. So we need to adapt it to make it contain only the selected features. So the idea is, first, we use a knee point to only select these promising individuals. And then we only adapt the promising individuals and reinitialize the remaining. This can speed up, make it efficiency. And how we adapt, we mimic the behavior, and we randomly generate a lot of individuals with only the select features. And we select the one closest to the individuals to be adapted. And the results are good. We can easily achieve much smaller program size, smaller number of features, and also achieve the same test performance. We can also see without feature selection, we can get much simpler and interpretable rules. Now, next we talk about the interpretable program structure. And this is to consider, the combination of the nodes. Some combinations might not be meaningful, so we should not consider them, like time plus length. So it doesn't make sense. So we should not consider that in our model. So we should penalize the uninterpretable combinations or subprograms. And this could be achieved by strongly typed GP, grammar-guided GP, and also ensemble GP. And this dimensionally aware GP is a kind of, considering the physical dimensions, such as time, length, the physical units. And this can be implemented by strongly typed and grammar-guided GP. So strongly typed GP can learn decision trees. Decision tree, we know, has a good interpretability. And here we can use GP to evolve this kind of non-orthogonal decision trees so that we can make it smaller, and each condition is also a linear condition which can also be easy to interpret. And we define the terminal set and function set into different types, like variable, constant, classification, different types. And grammar-based GP is, to define this grammar so that when we generating the trees, we follow this grammar. And some examples, if we want to evolve regional polynomials, and this would be the grammar. If we want to evolve a model for the ideal gas law, we can use this grammar. And all of them consider, only the reasonable combinations of the nodes. If we use grammar GP to evolve decision trees, this would be the grammar. We can say, okay, tree, this is a tree, and it starts with if then else. And the first is condition, the second is tree, the last is tree, right? And also, or it can also be the class itself, directly predicting. And the condition can be a composition of other conditions, or just compare a variable with a threshold. And it could also be used as the association rule mining. And in this study, it has two grammars, one for rule extraction and the other is to do the rule selection. And compare with other approaches, actually quite promising results in terms of both effectiveness and model complexity. Also, some studies use Grammar GP to evolve job shop dispatching rules like this. Consider the job shop state, and different job shop states use different dispatching rules. And this is, can be consistent with the domain knowledge. And also for image classification or analysis, has this grammar-based or strongly typed GP. From the input, it has the region detection, feature extraction, feature construction, classification layers, and each layer has its own type and also operators. And another example study here is to use the canonical form. And the idea is, yeah, we probably can have linear layer and non-linear layer and then linear layer, back and forth to repeat, so that at least, the linear layers are easier to interpret. But at the same time, we also have some non-linearity to guarantee the accuracy or the power of the model. And actually reached quite promising performance and simple models in the symbolic regression problems. Okay, last is the ensemble GP. The idea is that instead of having a single large complex GP trees, maybe we can just get a group of small trees forming a committee, and they vote for the final decision. And we don't require each small tree to be perfect. They're probably just good enough, simple and good enough. But when they vote together, they can cover each other, complement with each other. So this is the ensemble learning. And each small tree could be easier to interpret. And we tried this ensemble GP approaches. We could use bagging, boosting, and cooperative co-evolution. The bagging GP, we just use the sequence process. We use different training subsets at each cycle to learn one rule into the ensemble, and the limitation is that GP could be slow to get each rule. And boosting, the limitation is that it requires, also it's slow, and also cannot use large training set because it's already slow. We should limit the training set size, and then it might lead to poor generalization. And CCGP co-evolve all the rules, and we use different subpopulation for each rule in the ensemble. And the limitation is that it might not be able to consider the rules can be complementary. And we did some experiments, and the results show that actually CCGP performed the bagging and boosting in our problem, the weak routing problem. But this is because bagging and boosting actually cannot get many rules in the ensemble, and also they are slow to get good rules. And the issue of the CCGP, as we mentioned, the rules are not complementary if we simply use the standard cooperative co-evolution. Diversity is not considered in the population, so we could explicitly consider the diversity by niching, and we define a niching GP to evolve a diverse set of population to form the ensemble. And we use the phenotypic distance. We compare the behavior of the GP trees and form the niche, and we delete the duplicated GP trees in the same niche. And the ensemble selection, finally, we sort the final individuals by fitness and include them one by one into the ensemble. And if they cannot improve the ensemble, we stop. And we can see we got quite good performance compared with both the simple GP and CCGP. So we can see the evolved rules. These are the rules in the ensemble, and they are quite tidy and easy to explain. Finally, we quickly explain the dimensionally aware GP. So this is considering the physical dimensions. For example, we have the energy and the square energy angle, float, and any other constant or terminals. So it doesn't make sense to add energy with angle. So we define this grammar to avoid that combination from happening. With this grammar, we can evolve, something like this, the evolved features, and these are all meaningful features. This dimensionally aware genetic programming consider more generic, dimensions. We can define any type of dimensions, time, length, or any other gravity, all these different types of dimensions. We use a vector to represent its units of measurement in each dimension. In addition to calculating the value, we also calculate the unit of measurement vector. For example, if we do the addition, we require them to have the same unit of measurement, x, y, z, and the sum should have the same. The Culling GP is based on this. So it is possible that if we cross over and the new subtree might not satisfy the condition of the unit of measurements, we have this penalty, goodness of dimension, and we use that as a penalty. And here we select two parents by tournament selection, and we generate many offspring, and we select the offspring with the best, violation, smallest violation of the dimension. For scheduling rule, this has some domain knowledge, so we can see that the terminals or state attributes have the time, count, or weight, the job weights. So we have different dimensions based on our domain knowledge, and we can set this as the dimensionally vector here. And we are using the constraint GP, so we use a penalty coefficient in the fitness to penalize the difference, the violation of the dimensionality consistency. And we also adapt this alpha over time. We got some interesting results, and we can say there's only 2 violations here. All the others are quite consistent dimensions, which is really good. Last, we have this GP with interpretability measurement learning, because we know that interpretability measure is subjective. This study actually want to learn the measure of the interpretability from the survey. For example, they consider simulatability and decomposability as the 2 measures of the model interpretability, and they just let people answer some questions in the survey, and then try to learn a linear model from the survey results. For example, from the survey, they get this so-called PHI, proxy of human interpretability value, and then you get the linear model related to program size, number of operations, number of non-arithmetic operations, these model properties or features. And from here, this is the learned features. And we can see that the linear model has a big absolute coefficient here, which is a number of consecutive compositions of non-arithmetic operation, and also the number of non-arithmetic operations. So this makes sense because this would make the models quite hard to interpret. And then they use this learned interpretability measure to learn GP model, and they got some quite interpretable GP models. And last, model learning with personalized interpretability estimation. The idea here is to make it interactive. If we cannot get a commonly accepted interpretability measure, we just make it interactive and let the users decide. So there's a user interface, and provide some example comparisons, which one you think is more interpretable, and the users will pick. And based on the feedback, they create a label and train a neural network estimator to predict which should be more interpretable. Okay, I think that's everything from me. Andrew will take over and continue to introduce the post-hoc interpretability and GP visualization. Thank you.
Thanks very much, Yi. Now I'm going to continue talking about post-hoc explainable GP and then GP with visualization. So we'll start off with, there we go, post-hoc explainable GP, which is broken down into global post-hoc explainable GP and local post-hoc explainable GP. So global and local approaches that have been proposed in the literature. So the first method we're going to talk about is this thing called GREX, or GP for explanations, essentially, rule-based explanations. And this is a post-hoc method, which is to say, in contrast to the methods you talked about, all of these methods are about trying to explain complex machine learning models that have already been created. So post-hoc after the fact. GREX involves a Boolean or decision tree to approximate a black box classifier. It uses a fitness function that has essentially three components. Firstly, the number of train instances correctly classified. Secondly, the number of validation instances correctly classified. And then also the size of the rule. So GREX are trying to find the rules that best approximate or give the highest accuracy compared to the original complex black box model. The reason we have train and validation here is because obviously we don't want to use a testing set, because we want to be able to save that to then finally evaluate how well the model generalizes. This alpha, beta, and gamma parameters here are just ratings, so you can say how important each of these factors is. They also use a further post-hoc simplification algorithm to remove introns. So introns being parts of a GP tree that don't have any effect on the output, they get removed after evolution is complete. And they found that outperformed existing non-GP rule-based extraction methods such as RX and TreePan. And this would be an example of the sort of rule-based decision tree that could be created by this approach. After this, Ben Evans, one of my former colleagues, in his master's thesis, created this sort of next iteration that used a similar approach but is multi-objective in nature. So as we've talked about previously, reconstruction ability or classification accuracy and interpretability are often conflicting objectives. It's very hard to perfectly reconstruct your complex black box model, but also be very, very interpretable. You know, you would expect that if you have this really complex neural network, that you can't just have A times B and get the same accuracy. You need a much more complex model. And so by using a multi-objective approach, we can then try and find the approximate Pareto front and look at the trade-offs between these two. You know, maybe there's a certain level of interpretability we require, and by looking at the Pareto front, we can find what level of reconstruction error we can achieve with that. And so they use essentially a similar approach to before, where you have your data, you split it into training and validation, and then you run this multi-objective approach trying to recreate the predictions of the black box classifier. It's important to note here that we're not trying to necessarily get the correct predictions in terms of the class labels. What we're trying to do is get the same predictions as the black box, because we want to understand the black box itself, not try and beat it. You know, we want to know why the black box makes incorrect predictions just as much as we want to know why it makes the correct ones. And yeah, it has a much better trade-off between accuracy and interpretability, because you can get this front or this set of non-dominated solutions. And it does have the potential to actually further improve reconstruction ability. So you notice that when recreating a training set, for example, the training set predictions, you can sometimes get better accuracy in the validation set, because perhaps by making a simpler model, it's more generalized and less prone to overfitting. And they found that, for example, a 4-layer GP tree can recreate the predictions of a 200-layer neural network. I mean, that's pretty impressive, but certainly it depends on the problem you're trying to solve and other factors, of course. But if we look at the proposed method here, compared to the simplified decision tree, and a normal decision tree and a Bayesian rule list, you can see that the proposed method has essentially very similar accuracy to the simplified decision tree, is more accurate than the Bayesian rule list, and still is less accurate than the full decision tree, but certainly is much more interpretable. So we can find that trade-off between these two goals. So that was our global methods. In terms of local interpretability, there's also been quite a few GP methods in this space. So the first being this thing called GPX that was proposed quite well in 2020, reasonably recently. And you'll recall that local interpretability methods are all about trying to explain a single prediction. And the way that GPX works is that you give it your single prediction. So for example, say this is the input you would like to understand, more in more detail. If we zoom in on this input here, then it would be this one here. And you can see it's right along the border between two classes, between our red triangles and our greeny blue circles. And what this method does is it will generate a set of samples around that input based on a multivariate Gaussian distribution. So essentially adding some noise to it, and that will give us this set of samples or neighbors, as often referred to. And then we try and train or find and explain a model that's easy to interpret and that can mimic the behavior of the original model. So if we have our set of samples here for the point we're trying to explain, we know what outputs that will give on our original model. And then we can try and train a simpler model. So for example, a linear model or maybe a very simple decision tree to try and get the same predictions. And by doing that, we can then try and understand the explained model. And of course, here they're using GP to do that, evolve that explainer model, such that minimizing the error between the GP model and the complex black box model. And by using GP, which we know has the potential to be explainable, we can then look at the tree and try and understand what the most important factors at play are in that prediction. So for explaining random forest deep neural network support vector machines, they compared with Lyman decision tree and found that overall they would get better error on the regression problems, and also the GP trees were explainable. So on the Boston regression dataset, for a given input point, maybe we're trying to explain again a one particular input. GPX, their proposed method, produces a tree like this, which is showing you that the pupil to teacher ratio, so PT ratio, is important in this method, and there's also another factor at play here, and there's some scaling element to it as well. But for a different input point somewhere else in our data set, we still see that this is an important factor in a decision, but then there's these two factors, so different parts of the data set that are important for that particular case. And this is kind of what you would hope to see. Your machine learning model is making different decisions in different parts of the space based on different factors. And by doing a local interpretability approach with GP, you can then understand what those might be. All right, another one that did basically a symbolic regression-based approach was what we call ELA, or explanations by local approximation. And this was almost doing the opposite approach, in that this is trying to explain GP methods. So GP symbolic regression is actually, as we know, is a very good and promising approach to doing symbolic regression, perhaps state of the art even. But the trees for GP-based symbolic regression tend to be quite big and complex and hard to understand. And so how can we then understand how these trees are working? Again, from the perspective of local explanations, how do we understand the prediction for a single instance? And it uses kind of a similar approach. So for a given input that we would like to understand, X, we find the neighbors of X, some K neighbors in the feature space. And then we fit a linear regressor to find a function that best fits those K points. So we're taking this very complex GP symbolic regression method and then trying to recreate the prediction in a linear way using a linear model for part of it. to understand its behavior. And then we can interpret that linear regression model by looking at the coefficients or the importance of each feature. So this figure here kind of gives you an idea of how it works. If this black line is our real models, this is a true symbolic function. And we know that different GP tree depths will give us different performance. Say we have a depth of 6, that would be our red dotted line here. And you can see it approximates the true or the real function reasonably well, except for these parts in the middle where it doesn't quite have enough degrees of freedom to do it justice. But let's say we're trying to explain this red dotted line. If this black diamond here is the test point, this is the instance that we want the local explanation for, and then this would be our red line here. This bold red line here would be the linear regression prediction, the local explanation that we would get for that point. And you can see that line quite accurately estimates this curve formed by a dotted red line here. And they found that they got similar root mean squared error for both their EOA method and the original GP method. So the linear approximations were locally accurate. So if you're looking at a local scale, and then linear approximations are often quite more than sufficient for capturing the patterns that your model is forming. And you can even take this one step further and form global explanations of sort of stacking these local explanations. For example, they looked at the wine dataset, or a wine dataset, where the target was to predict the quality of the wine. And by doing a local explanation for every point in your dataset, you can then stack up the findings and look at the patterns across different class labels, or in a regression example, different, across the continuous target space. And it gives it's quite nice and interesting pictures where you can see what factors of the wine are most important for determining the quality of wine at different levels of quality. So when you have very high quality wine, for example, an 8-star wine, I don't know what the scale is, or very low quality wine of quality 3, then the acidity is important. So you expect very good wine to have a reasonably narrow, from my limited understanding, range of acidities, and then for low quality wine, you probably expect that the acidity is not what it should be. And so in those extremes, the acidity is really important. And also the sulfur dioxide, there's a relationship to acidity there. So as you have acidity being more important, sulfur dioxide is correspondingly less important in the predictions. And without going into too much detail, this is sort of what's supported in the viticulture or the wine literature. All right, so we're now going to talk about our final type of explainable GP, which is GP with visualization. And that's broken into two main categories, which is firstly the use of GP to create explainable visualizations. So can we understand the visualizations created using a GP approach? And then secondly is visualization to explain GP itself. So how can we understand how our GP algorithms work and function based on using visualization to better understand them? Yeah. So we'll start off with explainable data visualization. And we'll first talk about this idea of using manifold learning or GP-based manifold learning to do interpretable visualizations. And this was something that myself and my co-authors proposed a few years ago now in EuroGP. We're essentially this idea of manifold learning. We're trying to take a mapping from some very high dimensional data set to a much lower dimensional data set can be applied for visualization tasks. So if you have a 1000 dimensional data set and you push it down to 2 or 3 dimensions, and then you can plot those and visualize the embedding or the compressed space. And you may have heard of these methods before. So things like PCA is not strictly manifold learning, it's a linear approach, but very much dimensionality reduction. MDS, multi-dimensional scaling, t-SNE, and all these sort of things. But all of these approaches are very much not interpretable. PCA is to some extent because it's linear, you can look at the coefficients, but if you have a very high dimensional space, you have a very large number of coefficients. And so we can't actually understand where these embeddings, this low dimensional space is coming from. how do we get from this high dimensional space to a smaller one? And in this paper, we propose the use of GP for manifold learning, GP-MAL, as a multi-tree approach to do this. So if we have 2 or 3 dimensions in our embedded space, then we'd have 2 or 3 trees that take our high dimensional features and map them into our new lower dimensional space. And in this work, we use a fitness function that tries to preserve the neighborhood of our high dimensional space in the lower dimensional space. And that's sort of core to a lot of these methods, is this idea of preserving neighborhood, preserving topology of the manifold. And we found that we could actually achieve better data separation or higher accuracy on some data sets, while also making trees that are potentially interpretable. So again, these are symbolic trees, we can potentially interpret them. So if this is the dermatology data set, and here's our proposed method, our GP-MAL, compared to PCA, MDS, locally linear embedding, and t-SNE, we can see that our proposed method actually separates the classes quite well. And keep in mind, this is an unsupervised learning method. It's not using the class information. This is just plotting the data after the fact to see how the structure is preserved. Whereas things like PCA and MDS very much can separate the data, but not nearly as effectively or as keep it as spread out or into clusters in the same way that GP-MAL can. And this is the 2 trees that correspond to the 2 axes of this data set. And you can see, for example, this tree here is a very small one, but equally can be very much understood. And so this really highlighted the potential of using GP for visualization. And we sort of expanded on this idea further, primarily for visualization in this paper, by taking inspiration from t-SNE. So t-SNE at the time was very much the state-of-the-art visualization method. And so what we did is we took the cost function, or the measure of embedding quality, dimensionality reduction performance from t-SNE, and used it as one objective of a multi-objective GP approach. So we had the objective of how good a visualization was, and then a second objective, which is basically how big our GP trees are. So again, that trade-off between performance and interpretability. And I won't go into the details of the fitness function. It's based on KL divergence. So again, this idea of trying to maintain topology or the distribution of the data from the high dimensional space to low dimensional space. And just as a reminder, the reason this is a good idea is because t-SNE is very much this opaque method. It gives you an embedding, that gives you visualization, but it doesn't tell you how it got there. Whereas GP can tell you how it does that mapping. And so if we use this visualization method's cost function, which has good performance, and also look at the complexity of our GP trees and find that trade-off, we can perhaps get the benefits of both. And indeed, we found that this gives us better results than our previous GP-MAL method, though certainly, and this is not unexpected, it's still not as good as t-SNE in a lot of cases. Because t-SNE doesn't need to, discover this mapping, it can optimize the embedding much more directly using essentially gradient descent, and therefore often gets higher accuracy or better embedding quality. But of course, that's at the expense of not having that interpretable mapping. So you can see here that, for example, this would be a very complex but highly performant GP t-SNE method, where you can see the visualization is quite clear. It's got a cost of 0.107 compared to t-SNE, which is 0.105. So here we're minimizing costs, and these are both quite similar, whereas GP-MAL had a much higher cost, and this visualization is doesn't separate the green and the red classes nearly as well. And we see similar patterns across the data sets. But what I will also note is that in this example here, where we have a complexity of 34, i.e. 34 nodes across the 2 trees that form our visualization, the cost is certainly higher, but it's not dramatically higher, right? And so we're able to get very much what looks like a similar visualization at a much lower complexity. And so we can find that trade-off. We can look at those curves and choose that best point, which is what we did. Look at my picture getting in the way today. Look, that's what we did here. So we have, this is the sort of approximate Pareto front you get, where you have complexity along this axis and then cost along this axis. And this is zoomed in on this smaller, more interesting part of the front. And we can see that as we increase the complexity from very small to sort of 2550, our cost rapidly goes down, but we quickly start to reach the point of diminishing returns, especially at these very high complexities where we're not getting much more improvement for that added complexity. And we can see that in these pictures as well. So this would be a complexity of 19 because there's 19 nodes across these two trees, which would give us this visualization. This being a complexity of 33 nodes gives us this visualization. And this visualization has this visualization has a better embedding quality than that one because it better preserves some of the structure. And if you look at the original paper, there's actually a video that shows you how these all change over time as you increase the complexity. Another approach that was proposed was this method called MOG-PFEV, and this used again a multi-objective approach to balance classifiability and visual interpretability. The main difference here is this was a supervised learning method, so they use the class labels and perform classification as one of their objectives. So not unsupervised, but very much is focused on trying to separate classes and show how they are separated. And they use a variety of different clustering-based visualization methods and got plots like this where you can see how the class is separated and also understand the classification accuracy. Another approach was MO3GP, which was the multi-objective GP projection pursuit method. And this used 3 objectives rather than 2. So in addition to classifiability, again, a supervised method, as well as visual interpretability, they also use semantic interpretability. So things like how big the trees are, how functionally complex they are. And one of the particularly interesting aspects of this was they later performed a user study to compare to human perspectives on interpretability. So looking at how well their measures lined up with what test subjects thought. And if you compare to PCA, MDS, and MDA, you can see that this method here, the supervised method, which of course is using the class labels, can make much simpler models and also get very good separation of the classes. So the other intersection between visualization and GP is using visualization to explain GP itself. That is, how can we understand the performance of GP or how it searches and learns through visualization. And of course, we have very much these sort of classic approaches that we see throughout the GP literature, looking at things like convergence curves. So, you know, how quickly do the methods converge over time? If we can visualize them in this sort of way, we can understand, for example, how long we might need to train them for. Looking at things like entropies, so how diverse population is across generations, edit distance, genotype diversity, all these different methods of diversity that could help us understand the search and how well it's searching. In addition to this, we also have other, I suppose, slightly more sophisticated approaches, including what is called DU maps, which is diversity and uses maps, which was proposed in 2018, where they use heat maps to try and visualize both the diversity of the population and also the contribution or the usage of the genes, for example, subtrees or genes in a GA type of representation in the overall model. And by using this visualization approach, you can then compare the behavior of different GP methods. So, for example, if we look at diversity, how varied our population is across the generations, we can see that GE here is grammatical evolution, and then there's different variants of that, as well as the geometric semantic GP. So looking at different types of GP, we can see the SGE method here has a lot of diversity in sort of the first 10 generations, but then the diversity very much disappears after that. The gene index here being each of the elements of the genotype. Whereas something like GE or WHGE here, the diversity stays around much longer, and you can see there's diversity popping up even in later generations. Which infers that perhaps it's exploring the search space more effectively than the SGE or the GSGP methods. In contrast, the uses maps visualizations are showing us what parts of the genome are most important in the final output of the model. So we can see, for example, on our genetic evolution here, that the whole, a large part of the genome is being used in that final evaluation. Whereas again, in the SGE here, there's only small parts of the genome that are being used throughout the whole evolutionary or learning process. And by then plotting each of these in a different color tone, we can look at the performance or the diversity and usage across both of these factors. And this then allows us to understand the search or different search patterns of these methods, and perhaps better understand how to improve them further. Another approach that has been proposed is in the optimization space, trying to understand how a population evolved during the GP process. And they did this by visualizing the phenotypic representation. So phenotype being the structure, or sorry, not the structure, the outputs of the GP trees, and trying to visualize this across the evolutionary search. So they use quite a standard GP loop here, but when they evaluated it, in addition to updating the fitness and so on, they also did dimensionality reduction on the phenotype, so the output of a tree, and then use what is called a grown neural gas algorithm to try and visualize how these are spread across and related in the graph structure using coloring and labeling. And what they found is that different parameter settings for GP will give very different results. So if you have a very high or a reasonably normal crossover rate of 80%, then you start to see trends in the structure or the diversity at around 10 generations, and then convergence very much is quite quick after, say, 20 generations. So at the very start of our evolution, these red points, so the red being very poor performance or low fitness, we can see there's very much spread all around our search space, which is what we expect when we randomly initialized our population. By 20 generations, there's many more points around the green space. So the bigger the points, the more individuals that it represents. And then as we get further and further along, by the time we get to 40 or 50 generations, very much the search is converging. Whereas if we flip that around and instead use 80% mutation and 15% crossover, the convergence, as we would expect, is much slower. So at generation 20, you can see there's a much bigger spread of individuals throughout the search space. And in fact, there's actually green points, not just in one area, but in different areas of this graph. Though it still does converge in the end to that sort of final optima, much like the previous method did. So higher mutation, higher exploration, and by using a visualization approach like this, we can validate and again better understand the search process. We can also see how the population moves. So if we have subpopulations, so more than one population in our search, we can look at, for example, the first population, perhaps it starts over here and then moves throughout this graph like this to reach the final solution. And again, that can also allow us to see the search process and how much diversity and other things like niching that we have going on. The final thing we're going to talk about in this tutorial is some of the challenges and future directions in the explainable GP space. As you can imagine, it's quite a new field or quite an emerging field at the moment. And so very much there are a lot of challenges and really interesting directions that you and everyone in the field could certainly be researching further. So firstly, one of the big challenges is how we actually measure this idea of interpretability. So why is some GP program more interpretable than another one? Why is A more interpretable than B? And this is inherently subjective, right? Like what is interpretable to myself and you is very much different to what's interpretable to somebody who doesn't is not familiar with machine learning or computer science more generally. And a lot of the current XGP literature uses proxies such as tree depth, number of nodes, model complexity, measures of the size of trees, and or other sort of measures of complexity. But it's not clear, and it hasn't been demonstrated in the literature, that these necessarily reflect human views particularly well. You know, to us, it's obvious that a smaller tree is the better, and I think we can all agree on that in the general case. But what is the trade-off between these things? What is actually more important? A big tree that uses only addition and subtraction, or a really small tree that uses piecewise operations that are harder to understand? And yeah, interpretability is very much dependent both on your technical expertise, but also your cultural background, your worldview, you know, what you're comfortable talking about and how you understand the world and how things work around you. There has been some initial work used in human studies to look at some of this thing, but certainly there's more work needed. And very much this whole idea of understanding interpretability is itself cross-disciplinary. So drawing on things like the cognitive sciences, social sciences, psychology, all of this is really important in trying to understand or trying to interpret what is interpretable. And I think there's a lot of really interesting work at the intersection of these research fields. For example, there's many different aspects of interpretability. And this paper by Tim Miller, which draws on the social sciences, is a really interesting deep dive into perhaps some of the things we should be considering when we talk about interpretable methods. For example, an explanation of a model that we are trying to interpret or explain, often the user is more concerned about why one event happened instead of another. So we want explanations that are contrastive. Why didn't I get a loan instead of getting the loan? Or why am I earning $30,000 when my friend is earning $50,000, even though we're doing the same job? Explanations also need to be selective. So sort of counterintuitively, a lot of people don't actually want the perfect explanation. You know, it's not, we get very focused on finding the optimal or the best solution in computer science, but in many cases, an explanation that's good enough, but simpler or more tuned to the individual person is more likely to be accepted than the absolute correct one in an algorithmic sense. And similarly, humans do not really think in terms of probabilities. So saying that there's a 79.4% chance that A causes B, or that is much less important than the A causes B part. So using probabilities and, you know, sort of scoring and so on is often less important than just talking about that causal relationship itself. So you were denied a bank loan because your income was too low, rather than you were denied because your income, you know, was not within the appropriate range with some probability. And also the final point made in this paper was that explanations are social, or they should be social. So humans, much as I'm trying to do now in a monologue form, interact and think through discussion or questions and answering. So if I provide you with an explanation as to why something occurred, a very natural response on your part is to say, well, I don't quite agree with that part, or can you expand on this aspect in a bit more detail? And so building algorithms that can do that, that can then fine tune or give an answer to follow-up questions, is also really important in making these models truly explainable. And as we talked about throughout this tutorial, the trade-off between interpretability and accuracy is a really hard dynamic to balance. We know the most accurate model is almost never the most interpretable model. You know, if you have 1 billion parameters in your neural network, you probably think that'll be more accurate than a perceptron. and the perception is never going to be as accurate as the very complicated model. It's also really hard to balance these two things during the GP search process itself. For example, a GP tree that's really big is much easier to optimize than one that's really small. And also a tree that's really big is much harder to simplify. So you kind of get this difficulties in your search process in that your search will create very big trees and then not be able to make them smaller because they're so hard to cut down because there's so many parameters involved that are interacting, or you'll get very small trees that are very hard to improve your performance on because you don't have enough coefficients or free parameters. And as we all know, doing multi-objective optimization itself is hard. You know, we talk about two objectives here, interpretability and accuracy, but very much based on different measures of interpretability and different measures of accuracy, it could be a mini objective problem, and then that just sort of makes it even more challenging. So in conclusion, in this tutorial, we talked a whole bunch about Explainable GP, and we talked about the different types of interpretable AI, intrinsic and post-hoc, global and local interpretations. And I hope, if anything, we've really highlighted the potential of GP in this area. You know, we're given this tutorial because we actually believe GP is a really powerful and valuable method in the explainable AI space, and we want more people to do this research and to move the field along. It's a really interesting area to be in. So we'll leave it there for today. There's our websites if you want to see some of our publications and also our research group. And very much, Dee and I are happy to answer any questions as well. And thanks very much again for attending.